Today, let's delve into alternating series. Let's consider the following cases. How about the second case? The first series can be represented as follows. The second series can also be represented in this way. Alternating series can be expressed in the form of AAN equals -1 to the power of n times Bn, or -1 to the power of n-1 times Bn. It can be observed that the general terms of the second and first series follow this pattern. Here, Bn is always positive. In an infinite series where terms alternate between positive and negative, if the terms decrease or stay the same as n increases, and the limit of the general term approaches 0, then the given alternating series converges. This is known as the alternating series test. If we represent this process briefly on a number line, we start with the first term b1 and denote its sum as s1. Subtracting the second term b2 gives us the sum s2. Adding the third term b through 3 takes us back to the right, forming s3. Subtracting the fourth term b4 moves us back to the left, resulting in s4. Adding the fifth term b5 takes us right again, yielding s5. Subtracting the sixth term b6 returns us to the left, giving s6. This alternating motion continues, converging towards some central value, thus demonstrating that the alternating series converges. Let's consider the following case. If we take Bn as 1 over n, it's always positive. Looking at the relationship between Bn and Bn plus 1, we can see that the terms decrease as n increases. Additionally, the limit of the general term is 0. Therefore, according to the alternating series test, we can conclude that this series converges. Let's consider the following example. If we express it as an infinite series, it would be as follows. If we take Bn as n plus 1 over n, then Bn plus 1 becomes n plus 2 over n plus 1, and we can confirm that the terms decrease as n increases. Okay. Now let's check the limit of the general term. The limit of the general term is 1, not 0. It doesn't meet the condition. Therefore, we can conclude that the given alternating series diverges. Let's consider the following example. If we express it as an infinite series, it would be as follows. Let's examine the series of absolute values of the general terms. The absolute value of the general term is 1 over square root of n. This has the form of n raised to the power of p in the denominator, where p is 1/2. According to the p-series test, we can conclude that it diverges. Although this series actually converges in such cases, we say that the series is conditionally convergent. Let's consider another case. If we express it as an infinite series, it would be as follows. Let's examine the series of absolute values of the general terms. The absolute value of the general term is 1 over 3 to the power of n. This is a geometric series and converges. This series actually converges as well. In such cases, we say that the series is absolutely convergent. Let's summarize. Absolute convergence and conditional convergence of alternating series describe two situations regarding how a series converges. If the infinite series of the absolute values of all terms of the given alternating series converges, then we say that the series is absolutely convergent. If the given alternating series converges, but the infinite series of the absolute values of all terms diverges, then we say that the series is conditionally convergent. See you next time.